Hey, before I talk into the meat of this video, I'd just like to mention that I don't need the pedal I'm building, and I'd like to pass it along to someone watching this. If you want a chance to receive it, just hit my email, listed below, with evidence of recent charitable activity like volunteering or donation, obviously sanitized of sensitive information. Once I've got a good handful of applicants, I'll randomly choose one, maybe even on stream, and if you're selected, I'll contact you to let you know, and so long as you can cover the cost of shipping, it's yours. I will exercise some discretion in terms of accepting applicants, but rest assured that no charity is too small. $5 from someone with almost nothing means more than $100 from someone who's got almost everything. I'll take this preface down once the pedal is accounted for, so if you're seeing this, you still have a chance to get in. Hi, I'm Zach, the guy behind Saturation Sound, and this is a build walkthrough and circuit explanation of the Floor DIY board. This is a bass shaping EQ-ish circuit. It's a little over-engineered for its function, but it uses some useful circuit concepts, which I'll touch on as we go through the build. First part of the operation is the power supply. So starting with the 9-volt rail, the first component that we come into is diode 1. I recommend you use something like the 1N5817. It's a Schottky diode with a very low forward voltage drop, so I'm able to use it just directly in line with the DC input jack as a reverse polarity protection. Next we use this 4.7 ohm resistor, and that just helps with the ripple filtering in conjunction with the main filter cap, which we'll be getting to next. Here is that aforementioned filter cap. It's a bit of a beefy boy, I spec'd 100 microfarads. You can probably get away with less, but sometimes there's no kill like overkill. The leads on this one are a little funny, so I do have to walk it into the board a little bit. Next we get onto the 4.5 volt supply. So to achieve this, we're just using a simple voltage divider with a ratio of 50%. And for that we'll be using these two 10K resistors. So the top resistor connects to the 9-volt plane, and the bottom resistor connects to the top resistor and the ground plane. And the node in the middle gives you your 4.5 volt reference. Next we need this second filter cap. I specified a 47 microfarad, but you can get away with less. Do take some care when you're populating these electrolytic capacitors because they are polarized. If you install them backwards, they can explode on you. If you look on the board, the holes are marked with a positive and a negative. The positive lead on the cap is longer, and the negative side is marked with, in this case, a gray stripe, and sometimes negative symbols, in line with the negative leg. The pad on the positive hole is also square for easy identification. When your components are populated, it's good practice to bend and crimp over the leads so you have mechanical support to the board. Sorry, my hands are right up in your view, exposing my subpar skincare occasionally. I promise I'll get better. Once your leads are crimped over and splayed out like the legs of a dead bug, just take your trusty little side cutters and trim off the excess. Once your leads are crimped and trimmed, then it's time to solder them. The aim is to heat up the pad and the remaining component lead, and then just flow the solder into the heated area. I personally like to only do one lead of a component at a given time and move around the board if at all possible, just to help manage the thermal stress applied to everything we're working on. Oops, I didn't like that connection there. Only doing one lead at a time does help preserve the life of some of your more sensitive components like semiconductors. Still wasn't happy with that one. Before we go into the rest of the circuit, I will be installing the socket for the quad op-amp chip. This socket has a pin 1 indicator notch, which should correspond to the little diagram on the board silkscreen. That notch helps you orient the op-amp when you finally install it, because if it is not installed correctly, the pinout might not be correct and you might either kill the op-amp or just the circuit won't work correctly. This is the op-amp we will be eventually installing once we finish. I like to install that after all the soldering has been complete, for the aforementioned reasons. All throughout the circuit we'll be using a lot of these 1 microfarad capacitors, and we'll be using one of them right now for the input of the circuit. This first 1 microfarad capacitor is the input coupling cap. It helps separate the input of your circuit, either your guitar, bass, or preceding effects, from the bias voltage that is needed to operate the operational amplifiers. This 1 meg resistor here is a pull-down resistor, which helps bleed off any charge that builds up on the input coupling cap, and helps minimize switch popping. Now we get to this first op-amp stage. It's very simple and it's just configured as a buffer, or a voltage follower. So for it to operate, we need this 1 meg resistor, which connects to the 4.5 volt bias supply. The bias supply is important because the op-amp can only reproduce voltages between its supply rails, in this case 0 to 9 volts. But your input signal swings around 0 volts, so it has negative voltages. The bias reference shifts that operating point up to be swinging around 4.5 volts to actually allow the op-amp to reproduce the input signal. This first op-amp, in addition to being a buffer, also serves as a signal splitter, and we'll be sending a copy of the input signal through this 100K resistor marked on the board as M10 to op-amp 4, the final mixing stage. Next, we get into the main filter itself. This is a Sallen-Key topology filter. It's an active 2-pole filter design with an optional resonant behavior. I'll include a link to the Wikipedia page so you can read up more on it. You tend to see these more in the world of synthesizer design, but I tried it out for use in my bass utility device, and I thought that sounded really cool, so I repurposed it for this circuit. So the first thing that we need are these two 4.7K resistors. To complete the filter, we do need these two 220 nanofarad caps marked on the board as U22. I have to own up to a bit of an error that I made in the board layout. I forgot to connect one of these caps to the ground plane, so I had to bodge in a little jumper. I'll fix that for subsequent generations of these board, but the first 10 are going to have my little rework on them. Now, the Sallen-Key filter relies on an active amplifier, in this case provided by op-amp 2. And the resonance is governed by the gain of this amplifier, and that gain is governed by these two resistors here. Now, the way that gain works in op-amps is based on the property that they want to see the same voltage at both input terminals. We achieve this with negative feedback, connecting the output of the op-amp to the inverting input terminal, and using resistive voltage dividers to attenuate this feedback signal. The smaller the feedback signal, the harder the output has to work to equalize the signal seen at both outputs. So in this case, the top of that resistive voltage divider is provided by this 33K resistor. If you want to increase or decrease the resonance of the filter, you can play with these values, but you should take care because increasing the gain and thus the resonance too much can cause the filter to what we call self-oscillate. It might be a little more experimental than what you might want. Or maybe you do. Like, I'm not the boss yet. The voltage divider is completed by this 22K resistor. And to really complete this operation, we need this 1 microfarad capacitor here, which actually blocks off the bottom of the voltage divider from the ground plane, only allowing the AC portion of the signal to be attenuated. If you omitted this capacitor in the design or jumpered it on this board, the circuit might malfunction because the bias signal, or because the bias voltage would also be attenuated. So the output would have to consequently increase the DC portion of its output to account for this, and potentially push the output signal beyond the power supply available to the op-amp, which would either distort or possibly even just outright kill the musical signal that you want to hear. After the active filter stage, we got into this mess of components right here, which forms what I'm going to refer to as an attenuverter, which is another carryover from synthesizer world. This is basically another splitter amplifier, like you see on Op-Amp 1, except instead of two identical versions of the signal, one of those copies is reverse polarity to the other copy. But before we get to that, we need another voltage divider. Because we turned up the gain of the op-amp to increase the resonance, it does consequently increase the overall amplitude of the signal, which we actually do want to be unity gain to maintain a predictable behavior with the dry signal. So we achieve that with another voltage divider formed by these two resistors up here. This first resistor is a 330K resistor marked on the board as M33. And the voltage divider is completed with its 220K resistor marked on the board as M22. Now, because I want to preserve the DC operating point because I find that it biases the following transistor nicely, I'll be doing the same capacitor trick as I did with the op-amp gain. With this, again, you guessed it, 1 microfarad capacitor, which connects the bottom of the voltage divider to ground, thus AC coupling it. Now this splitter inverter was a trick I borrowed from the Green Ringer, which uses a transistor amplifier in a similar way. It works because a transistor's output can be tapped at either the emitter, which produces an output at the same amplitude and polarity as the input, or at the collector, which produces an output with opposite polarity as the input, with the gain determined by the relationship between the collector and emitter resistors. With that out of the way, we get to the transistor itself. I'm specifying a general purpose BC547. It's a common NPN transistor. You do need to be careful of the pinout. On this particular package, the leads go collector, base, and emitter, which corresponds to the little schematic symbol that I have on the board, which goes collector, base, and emitter. To further help with identification, the collector hole is marked with a square pad. I arranged the pads in this triangular configuration to maximize flexibility with the potential for different pinouts. To complete the transistor amplifier, we need the collector and emitter resistors. In this case, we're using 2.2K resistors. If you use a different transistor, you might need to tweak these values somewhat. But so long as the two resistors are identical, the transistor amplifier on the collector side will have a gain of 1, which is important for maintaining the symmetry of the base shaping effect. Finally, we don't want the DC components of the outputs to potentially interfere with each other, so I'm using these two 1 microfarad capacitors here to block the DC portion of the signal. Now, in your build, I would actually recommend that you do this part last, but just for the sake of following the signal as it would pass through the circuit, I'm going to do it now. My suffering for your education. So we're first going to prepare some leads to connect the potentiometer to the board. These leads don't need to be particularly long, just a couple inches. I'm using some wire strippers to just break the insulation at each end of the lead. And then I twist and pull those broken ends off to twist all the strands together in a nice, convenient single motion. And then just flow a little bit of solder into the braided strands to tin the lead. Now, because this is a slightly larger board, we do actually need to position the board on top of the pot inside the enclosure. To connect your leads to the pot, just bend over one of the tinned ends to form a little hook. Hook it through the lug. Crimp the hook shut around the lug. And then solder it to finalize the connection. So the way this pot works in the circuit is it's effectively panning between the two different outputs on the transistor amplifier. The outputs go to the outside lugs on the pot, and the middle lug, which connects to the wiper, connects to the following op-amp buffer. So as you move the wiper closer to one side or the other, it adjusts the balance towards either the positive polarity or the negative polarity signal. So when these signals are eventually mixed together with the original dry signal taken from the first op-amp splitter, the low frequencies will either constructively or destructively interfere based on their polarity, either giving you the bass boosting or bass cutting effect at the filtered frequencies. Snap off this little locator tab, because we're not drilling a little hole for it to socket into. We're not at that level of sophistication yet. Now, because the pot is going directly above the board, we do need to insulate the back of the board and its exposed solder connections from the conductive back of the pot. In this case, I'm using the bag that the pot was sold to me in, which just happens to be the almost perfect size for the back of the board. So I'm just going to quickly mark where the leads are going to go through. And take a little cutting implement and make a hole for the leads to go through. And the pot will pass through. Just like this. Now, you do have to pay attention to which hole which lead goes through. The lugs on the back of the pot are counted left to right as 1, 2, and 3, and the spots on the board for those leads are correspondingly marked 1, 2, and 3. The hole for lug 1 is also marked with a square pad. Next up is op-amp 3, which is, much like op-amp 1, a simple buffer circuit, which uses these two resistors here. That's all the components you need for this stage. Because of the blocking caps from the transistor splitter amplifier, we do need to restore the 4.5 volt reference, which we achieved through this 1 mega ohm resistor on top. This 100K resistor will be connected to the output, but we'll get to that in a second. Here is said 1 meg resistor, which we just plunk in up here. And here is that 100K resistor marking the board as M10. It's connected to the output of this op-amp and forms the mixer network that I mentioned back when we were doing op-amp 1, and connects to the non-inverting input of op-amp 4. Moving on to op-amp 4. The input has already been accounted for. It's just a passive resistive mixer network. Now, because this style of mixing attenuates the gain because of a voltage divider effect between the two inputs, we do need some makeup gain on this amplifier stage, which is achieved with these two 10K resistors here. Honestly, you can probably use smaller values for the 100K resistors, but it sounds fine, so don't have to worry about it. In my opinion. And much like with the gain set in op-amp 2, we need another 1 microfarad capacitor to avoid losing our DC operating point. Finally, we get to the output of the circuit itself. For that, we need the output coupling cap to block whatever follows this effect, C component of the output of the op-amp. And finally, one last 1 mega ohm resistor serves as a pull-down resistor to bleed off any charge that will build up on the other side of the output coupling cap and help minimize switch popping. In conjunction with good bypass switch wiring, of course. We can install the quad op-amp chip into the socket. In this case, I'm using a very common and widely used TL074. When you receive them, the leads tend to be splayed out a little bit, so to make them fit nicely into the socket, or if you're soldering directly onto the board into the pads on the board itself, you just have to place the op-amp on a flat surface and gently bend the leads inward so that they're close to parallel. Ensure that the op-amp is oriented correctly. Mark up the notch on the package with the notch on the socket or the notch on the silk screen to help ensure that pin 1 is properly lined up. Gently press the op-amp into the socket to ensure that you're not bending any leads inappropriately. And with that, the board is done. Now that we're finished, all that's left is enclosure prep and assembly. Already shown how to do this in the first build video of the Glass Booster DIY project, so I'll just add a card pointing to that video here. Note that this board is bigger than the glass booster board. I might have to move some bits around, like you can see on this finished device.